get that feeling that numbers have like a secret life of their own? Well, today we're going to crack their codes. We are diving deep and playing with numbers. I mean, it's a feeling a lot of us have had, right? That behind those simple digits on a page, there's this hidden language just waiting to be understood. And you know what? You're not wrong. Every single number has a story, and it's told through its own unique properties and patterns. So, for the next few minutes, let's put on our detective hats. Our mission, should we choose to accept it, is to uncover the clues that are hiding inside numbers and finally decode the messages they've been holding all along. Okay, so every good detective has to start with the fundamentals. For us, that means getting really good at two key techniques: breaking numbers down into their most basic parts, and then building them back up to see where they can go. First up, factors. Just imagine you've got 6 candies. Now you could share them perfectly with 1 friend, or 2 friends, 3, or even 6 friends, and you'd have none left over. Well, those numbers, 1, 2, 3, and 6, those are the factors of 6. They're basically the building blocks a number is made from. Now, on the flip side of that, we have multiples. If factors are all about breaking a number down, multiples are all about building it up. Picture a number line. If you start at 0 and just take jumps of 3, where do you land? You land on 3, then 6, then 9, 12, and you could just keep going forever. Each one of those landing spots is a multiple of 3. So, here's the big takeaway, the thing to really remember. Factors are finite. They're like treasures in a chest. You can count every single one. But multiples, they're infinite. They stretch out forever, kind of like the universe. One looks inward to what a number is made of. The other looks outward to what it can become. Okay, so we've got our basic tools. We're ready to go deeper. We're about to uncover the fundamental particles of the entire number world. You can think of them as the atoms of arithmetic, the things that all other numbers are built from. And here they are, prime numbers. These are the elemental particles of math. Numbers like 2 or 7 or 13. They're prime for one simple reason. They have exactly 2 factors, 1 and themselves. Not 1 factor, not 3. Just 2. That rule is absolute. So what about everything else? Well, any whole number that's greater than 1 but isn't prime is what we call a composite number. Think of numbers like 4 or 6 or 10. They all have more than 2 factors, which means they can be broken down even further. They are, quite literally, composed of other numbers. But wait, what about the number 1? Is the ultimate outlier, a total lone wolf. See, it only has 1 factor, itself. And because of that, it doesn't fit the rule for being prime, and it doesn't fit the rule for being composite. It's in a category all its own. And all of this leads us to one of the cornerstones of mathematics, prime factorization. It's this really profound idea that every single composite number, I don't care how big it is, has its own unique DNA, a very specific set of prime numbers that, when you multiply them together, create it. So how do we find this DNA? Our best tool is the factor tree. Let's try to crack the code for, say, 36. We can start by splitting it into 2 and 18. Now, 2 is a prime number, so we circle it. That branch is done. But 18, we can break that down again into 2 and 9. Another 2. That's prime, circle it. And finally, 9 breaks down into 3 and 3. And both of those are prime, so the prime DNA of 36 is 2 times 2 times 3 times 3. And the coolest part, no matter how you start breaking down 36, you will always end up with this exact same code. It's unique. Okay, now that we kind of get a number's atomic structure, let's learn some detective shortcuts. Think of these as number hacks or cheat codes that let you instantly see a number's secrets without doing a single bit of long division. Let's run through the basics real quick. A number is divisible by 2 if it's even, easy. By 5 if it ends in a 0 or 5, and by 10 if it ends in a 0, simple enough. But the rule for 3 is where it gets really interesting. All you do is add up the digits. So for 546, you just go 5 plus 4 plus 6. That's 15. And since 15 is divisible by 3, so is 546. How cool is that? It's such a simple little trick. All right, ready for the advanced codes? To see if a number is divisible by 4, just look at the last 2 digits. If that little number is divisible by 4, the whole thing is. For 6, you just have to check 2 things. Is it divisible by 2 and by 3? If yes to both, you're golden. The rule for 9 is a lot like the one for 3. The sum of the digits has to be divisible by 9. And my personal favorite, for 11, you take the alternating sum of the digits. For 1331, that's 1 minus 3 plus 3 minus 1, which is 0. So yep, divisible by 11. These shortcuts are like having mathematical X-ray vision. All right, detectives, we've gathered our clues, we've learned the secret codes. Now it is time to solve the case. We're going to use everything we've learned to tackle two of the biggest number puzzles out there, finding the highest common factor and the lowest common multiple. So, the highest common factor, or HCF, is just what it sounds like. It's the biggest number that divides perfectly into two or more other numbers. Let's take 12 and 18. The factors they have in common are 1, 2, 3, and 6. The highest of those? It's 6, so the HCF is 6. Think of it as finding the biggest, most important building block they both share. Then there's the lowest common multiple, or LCM. This is the smallest number that is a multiple of both of your numbers. Imagine two little lights. One flashes every 2 seconds, and the other flashes every 3 seconds. The LCM is the very first time they're going to flash at the exact same moment, which would be at the 6-second mark. It's their first point of synchronization. And here is the essential difference between them. The HCF looks inward or backward, finding the largest shared piece from their past. But the LCM looks outward or forward, finding their first shared destination in the future. One is about their common history, the other is about a common destiny. And now, for the final secret, the beautiful little bow that ties this all together. For any two numbers you pick, their HCF multiplied by their LCM will always be equal to the product of the two numbers themselves. It's just a perfect, elegant equation that shows you the deep, hidden symmetry at the very heart of arithmetic. It's just beautiful. You know, we started this whole thing by looking for a secret language in numbers, and I think we found it. A language of factors, multiples, and these incredibly important prime numbers. But this just leads to a final, much bigger question. If prime numbers are the atoms of math, what else are they building? Well, the answer is everything around us. From the unbreakable codes that protect our digital lives to the spiral patterns of entire galaxies. The detective work, it never really ends. So what will you discover next?